Okay, we're going to talk about H12I, predator and prey, and other real-life models. Um, so the first page and a half is explained by Ivy Podcasting, this video here. So I am not going to explain this part at all because I want you to watch the video. Uh, uh, from IB Vodcasting. So, although his handwriting is a little bit messy, so here is my uh, work from what he explains. Hit pause if you need to copy things down. Here is my work from what he explains. And once again, here is my work from what he explains. Hit pause if you need to copy this down. And lastly, I really like the way he talked about this in his video. I'm going to move this up. And especially what he said here, I thought it was very useful. Okay, so now let's do the examples based on his um, his video. Okay, so here is the lessons for example 12I. And it says find the two equilibrium points for the populations. So as our lesson from IB Vodcasting goes, they reminded us that equilibrium happens when the change of Q with respect to T and the change of P with respect to T, all of these changes has to be zero if we're at equilibrium. So I've got, so if I'm looking at for this part right here, so if I've got Q minus 2 times P, if I make that equal to 0, then either either P equals 0 or Q minus 2 equals 0. So if this is the case, then Q is equal to 2. Okay? All right. In the scenario where this is at equilibrium, then I would have 1 minus P times Q, having that equal to 0. So either Q equals 0 or 1 minus P equals 0. And then if I rearrange this, then P would equal 1. So my equilibrium points happen at 0, 0 and at 1, 2. Now, how do I know which variable comes first? It's alphabetical. Elemental P, Q, P comes before Q. Right? Okay. Using the equation to explain what would happen to the populations of the prey if the predator were absent. Okay, I'm just going to explain what I wrote down. So if the predator was absent, P equals 0, then that means there would never be any predators. So the change of predators would never change because there aren't any to ever begin with. So that means the equation explaining what happens to the population of the prey. So if P was equal to 0, then we just have 0 times anything is 0. And then here, if P is equal to 0, we're just left with 1 with Q and then minus PQ, which simplifies to Q if P is equal to 0. Okay? And the population of the prey would grow exponentially according to Q. Now, um, if the predators, um, sorry, what would happen to the population of the predators if the prey is equal to 0? In that case, we're going to make Q equal to 0. And if I plug Q equal to 0 here and here, then we're left with the change of P dt is equal to negative 2P. Okay? And then so the population of the predators would eventually die off. Okay. Let me just explain what I've written here. So if the initial population happens when t equals 0, and the prey is 2000 and the predator is 2000, use Euler's method with a step size of 0.1 to find the population at the end of each year. Okay, so here's the population of the change of predator. Here's the population change for the prey. So using these equations, I can write this as P subscript n equals Q subscript n minus 1 minus 2 parentheses P parentheses n minus 1. Remember, we're going to use Euler's formula. And then here, Q subscript n equals 1 minus P subscript n times Q n minus 1. Okay. So now I'm going to put this information, get it ready for my calculator. So we know this is 2000 and 2000. Now I had put 2000 in my calculator, and then I got this weird error, and it didn't work. The calculator couldn't handle a number this big there. So I put 2 instead of 2000, and then when I got to the end, I multiplied 1000 at the end. So anywho, so we've got, using our formula packet, for Euler's method, xn plus 1 equals xn plus h times the function. And so I just wrote it this way. So the h is 0.1, that's our step. And then I just rewrote this portion of the function right here. And when I typed into my calculator, and we got a step size of 10. Sorry, we had a step size of 0.1. So to calculate a full year at a 0.1 of a year, we had to n had to be 10. Right? Let's check the next one. Okay, so once again, find the non-zero equilibrium positions for the population of foxes and rabbits. Okay, so if the rabbits is 0, then using this equation here, x minus 2xy, then, okay, x is rabbits, right? So if I make x equal to 0, I'm left, well, first thing I did, to make it a little easier, I factored out the x. Okay, so if I make this factor here equal to 0, then we end up with y equals 1/2. And this for y is for foxes. Foxes are as 100 times this, so we have 50 foxes. When the fox population is 0, then I look at this equation here, and I can factor out the y. And so the other equilibrium point when uh, when the foxes is equal to 0 is when I make this factor equal to 0, and we end up with 0.833. Now, this is for the rabbit population when we make equilibrium. So when the rabbit population, and we multiply that by 1,000, when the rabbit population is at 833. Okay, these numbers are you're going to see them in a minute when we do the last page of this. Okay, so um, initially there was 750 rabbits and 100 foxes. Um, so state whether the population of the foxes and rabbits are initially increasing or decreasing. So here is my population change formula for rabbits. Here is my population change formula for foxes, which is from up here. Okay, so we're essentially putting in 0.75 in place of x and plugging in 1 in place of y. And then we get negative 0.75 in place for dx dt, which is the population change of rabbits at this time. So the rabbit population is going to be declining when the rabbits have this many and the foxes have this many. And then here, the fox population is going to be decreasing also when these populations are that way. Okay. From the differential equation, find the size of the fox population when the rabbit population is at a maximum. So maximums happen when a derivative is 0, right? We have turning points, and when a derivative is 0, if a derivative is positive, it's going up. When the derivative is negative, it's going down. And so when the derivative is 0, that means we have a maximum population for rabbits. So to figure out a maximum population for rabbits, we need to make the rabbit derivative equal to 0. And so if we do that, then the factors, so it's going to be at a population of 50. Okay, so so the fox population, when the fox population is 50, we have a maximum rabbit population. And that's going to show on the graph in just a minute. Okay, the size of the rabbit population when the fox population is at maximum. So the fox population is at a maximum when dy dt is equal to 0. Once again, if the dy dt is positive, that means we're getting more and more foxes. If dy dt is negative, then we have fewer and fewer foxes. So so when the fox population is the derivative is 0, that's when we're going to have our maximum rabbit population. Okay, so if feel free to. This GeoGebra tool is so amazing. You could type in your equation in here and then hit enter if you go to this website, and you'll get the same graph that I got myself. And so if you look here, I want you to notice that when the rabbit population is 833, it's going to be kind of like around here, okay? And when the fox population is 50, kind of like around there. And you may notice on this graph here that I created for this problem, notice how as when the fox population was at 50, so here the rabbit population is increasing, and then the rabbit population starts to decrease. Okay, increasing rabbit population, decreasing rabbit population. Here, decreasing rabbit population 50, increasing rabbit population. So at 50, it's either we've got a turning point here and we've got a turning point here. Same thing here. When the rabbit population is at 833 rabbits, the fox population here is increasing, and then the fox population starts to decrease. Okay, so both the rabbit and fox populations decrease until the foxes reach 50. Then the rabbit population starts to increase, followed by the fox population to 50. After that, the rabbit population decreases again until we return to the starting population. Okay, that's it. Please watch the IB vodcasting video.